Greetings and welcome to Chapter 4, Discrete Random Variables, Lesson 4.3, Binomial Distribution. When we're going through the next couple of chapters, we're going to focus a lot on different types of probabilities, distribution functions. And to do that, we really need to understand what values do we include in the calculation and what values do we exclude in the calculation. I have a number line going from 0 to 30. And if we wanted to know an example of, let's say we randomly pick a person and we ask them, how many pets do you have? And that person says, I have 3 pets. Well, what's the probability that I would have picked a random stranger out of a group and they would have said exactly 3 pets? Well, that's the probability that x equals 3. And so it is one value on my number line, and therefore I have one calculation, the probability that x equals 3. So P of 3. Now I pick another person out of random and I ask them, hey, how many pets do you have? And they kind of don't want to really talk to me, and they say, oh, I have at most 3. Well, here's the thing. At most, it could be they have 0 pets, 1 pet, 2 pets, and since it's at most 3, they could indeed have 3. And to figure out the probability that I would have selected a random person that said that they have at most 3 pets, that is 4 calculations. I do have to calculate the probability of 0, the probability of 1, the probability of 2, and the probability of 3, and I have to add those up, and that equals the probability as x is less than or equal to 3. Now I go through the crowd and I pick another person at random, and they say, I have less than 3 pets, or I have fewer than 3 pets. Oh, well, on the number line, they could have 0 pets. They could have 1 pet. They could have 2 pets. Not 3, because it's strictly less than 3. That's 3 dots on my number line, and yes, to find the probability that I would have randomly selected a person out of the crowd who would respond as less than or fewer than 3 pets, I would have to calculate P of 0, P of 1, and P of 2 and add those up. That equals the probability that x is less than 3. Now I go through my crowd again and I pick another person and they say, I have at least 3 pets. Now we've decided the maximum amount of pets that anybody has is 30. But because they said at least 3 pets, they could have 3 pets, they could have 4 pets, they could have 5, they could have 6, they could have 7, they could have all the way up to 27 pets, 28 pets, 29 pets, and 30 pets. And therefore, what's the probability that I would have grabbed a person that would say at least 3 pets? That means, yes, I have to calculate the probability of 3, the probability of 4, the probability they would have said 5, the probability of 6, ... probability of 28, probability of 29, and probability of 30. And in fact, that's 27 different calculations I have to do, plus the addition of adding them all up. That's a lot of calculations if I'm going to do this by hand. Now, what's the probability I reach out and another person I ask and they say, I have more than 3 pets, strictly more than 3 pets. Now that means they could have 4, they could have 5, they could have 6, all the way up to 28, 29, 30. They cannot have 3 pets because they said it is greater than 3 pets, more than 3 pets. And to calculate that, I would have randomly selected a person and they said that they had more than 3 pets, I have to add up all those probabilities. Probability of 4, probability of 5, probability ... probability of 29, Probability of 30. Yes, 26 calculations to get that value. Now here's the good thing. If we were to add up every single probability on our number line, probability of 0 plus probability of 1 plus probability of 2, all the way through probability of 28 plus probability of 29 plus probability of 30, we know when we add up all of our probabilities for a particular situation, it will add to 1. So when you do have those big, bulky calculations where you have to add up 27 different calculations, we could take the shorter route. So I'm going to take that probability of x is greater than or equal to 3, which had 27 calculations, and I'm going to do the opposite, the exact opposite. Now, if I highlight 3 through 30, what's not highlighted? 0, 1, and 2. And therefore, I just have to take 1 minus the probability that x is less than 3. So I cut down my number of calculations from 27 calculations down to 3 calculations with 1 subtraction. Likewise, if I have the probability that x is greater than 3, that calculation that had 26 different probabilities that I had to calculate, I can do the complete opposite and say 1 minus the opposite. The opposite of greater than is less than or equal to. So if I highlight 4 through 30, what's outside of that? 0, 1, 2, 3. And so I only need to say 1 minus the probability of 0 plus probability of 1 plus probability of 2 plus probability of 3. It is much, much shorter route to take, and I will get the correct answer. Now, just to finish this up, the probability that x is less than 3 also has an opposite. I could say 1 minus the probability x is greater than 3. And if it's probability that x is less than 3, strictly less than 3, then the opposite calculation that will give me the same answer is 1 minus probability that x is greater than or equal to 3. What you always want to do is try and figure out, well, how many calculations am I going to have to do? And I'm always going to take the fewer calculation route. I would not take the 26 calculations. I would do the opposite and take the 4 calculations. Okay, so I just wanted to do that. Another little tidbit is the TI-84 calculator always starts at 0. It cannot start, for example, the x is greater than 3. It can't start at the probability of 4. It will always start at the probability of 0. And therefore, doing the opposite in that instance is how we're going to do it on the calculator. These are calculator problems, but you still have to understand, when do I go straight forward and just hit the problem straight on, and when do I have to do the opposite to make my calculator do the work? Get to know the new terminology for this lesson. Click on each of the words, learn its definition and meaning. When you are ready, click Continue. I did say occasionally we will have new math symbols. Well, we've run into one. We need factorial, which looks like an exclamation point. How you would see it is that you would have a number and then the symbol of factorial. What this means is whatever that number is, you're going to multiply that number and every integer below it down to 1. So if you have 3 factorial, it would be 3 times 2 times 1. If it's 5 factorial, it's 5 times 4 times 3 times 2 times 1. It's a shortcut way of writing that. Now let's see an example, 6 factorial. 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. That would be 720. If you have, for example, 10 factorial divided by 4 factorial, do not reduce yet. You cannot reduce the 10 and the 4. These aren't just like normal fractions. And you can't just eliminate those factorials because one is on top of the other. You can't do that. First, you have to write it out, at least down to that factorial that's on the bottom. So here's how I would do it if I was doing this longhand on paper. 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial all over 4 factorial. And then the factorials, 4 factorials, are exactly the same, and therefore I can cancel those out. And I'm left with 10 times 9 times 8 times 7 times 6 times 5, which is 151 200. I will say, as much as it looks like factorials are a lot of work, the TI-84 Plus does have factorial in its arsenal of things to do. What you would do is click on Math, scroll over to Prob, P-R-O-B, and under Prob, the fourth one down is the factorial symbol. So you can click on, you could type like 6, then go to Math, Prob, 4 for factorial, divided by something else, and it will do the factorials for you. Longhand this is the way that you would do it. But on the calculator, most calculators that can do any major calculations like the TI-84 or the lower cousin of the TI-84, the TI-30, both of them do have this factorial built into it. Binomial experiment has 3 specific characteristics. The first characteristic is there are a fixed number of trials. We're going to say we're going to run this experiment 10 times, or we're going to run this experiment 30 times, or we're going to run this experiment 50 times. It also will go along with how many people that you have run that experiment with. We're going to denote this with N. So if we have 50 people that are in our experiment, then N is 50 because we're going to run this experiment once for each of those 50 people. Secondly, there are only 2 possible outcomes. It could be a success or a failure. There is no in between with binomial. It's either a success or failure, and that's it. We're going to let P be the probability of a success and Q be the probability of a failure. And since you only have 2 outcomes, a success or failure, P plus Q, the probability of success plus the probability of failure, must equal 1. In the trials, they're independent, and we repeat them using identical conditions, and therefore the probabilities don't change for a success or a failure. They remain the same. And therefore, those are the 3 things binomial experiment has. Fixed number of trials, only 2 possible outcomes, and each trial, all the setup, all of the conditions are identical. The outcomes for binomial experiment fit within a binomial probability distribution. And the random variable, X, will be the number of successes obtained in the N trials. So here are the values we're going to be using, or the variables we'll be using. X, that describes what we're testing. N, number of trials. P, probability of success. Q, probability of failure. Very briefly, I want to talk about a Bernoulli experiment. And Bernoulli experiment, it is a binomial experiment, except for one thing. There's only one single trial. N equals 1. Everything else is exactly the same, except N always equals 1. We're only going to test it on one person, one situation, one tree, one bird. Whatever we're going to do, it's going to be 1. Otherwise, the other 2 conditions still hold. 2 possible outcomes, success, failure, P plus Q equals 1. In the number of trials are independent, and we get to repeat with identical conditions and identical probabilities. For the binomial distribution problem, one of the hardest things is to pull out the elements to be able to plug it into the math to be able to do. Because let's face it, I am going to show you the long way of doing the math, but in short, if you are using the TI-84, you're just going to plug it into a function that's already built in. So I don't believe it's going to be the math that's the hard part. The difficult part, I believe, is pulling out what elements of the problem go under which variable and what type of distribution are you working with. So let's talk about this problem description. Approximately 70% of statistics students do their homework in time for it to be collected and graded. Each student does homework independently. In a statistics class of 50 students, what is the probability at least 40 will do their homework on time? Students are randomly selected. First, we need to figure out, is this a binomial problem? Remember, for a binomial problem, it has to fit those three things. Do we have n number of trials? Well, yes, we do. We are going to run this quote-unquote experiment several times. 2, is there only a success and failure? Yeah, either the students turn in their work or they don't. 3, is there a probability success? So is there a p-value? Yeah, there is. Now we got to figure out which each of those values are, but it is a binomial problem. How do we define x? I mean, what is it that we're trying to test here? We're trying to see what is the probability at least 40 will do their homework on time. So x will be the number of statistics students who do their homework on time. What values does little x take on? So big X is the number of statistics students who do their homework on time. What is the value of little x? We have 50 students in our class, so our little x can take on the values of 0, 1, 2, 3, 4, 5, so on and so forth, all the way up to 49, 50. We know what a success is, but what is a failure? What does it mean to have a failure in words? If a success is doing homework on time, then a failure would be not doing homework on time. What's the probability of success? Generally speaking, in your problem description, you will be given the probability of success. And in this case, approximately 70% of statistics students do their homework in time for it to be collected and graded. So the probability of success is 70%, but we don't do math on percent, so we need to change that over to a decimal. P, the probability of success, will equal 0.7. What's the probability of a failure? Remember, probability of a failure is Q, and we do know that P plus Q equals 1, and we know what the value of P is, 0.70. So that means Q must be 0.30. So we have figured out N is going to be the 50. We know what P is, that's 0.70. We know what Q is, that's 0.3. And we know our X values are going to be 0, 1, 2, 3, all the way up to 50. So we have all the parts and pieces we need to actually do the math behind the scenes. The calculations are fairly straightforward, at least for the mean, the variance, and the standard deviation. It's when we get into the actual probability portion of it, it looks crazy, but actually it's not. So just hang tight with me. Mu is calculated as n times p. Yep, that's it. Take the number of trials you have, for example, in our previous one, which was 50, our probability was 0.70. You multiply those two together and you get your average mu. Your variance, which is sigma squared, is n times p times q. Yep, that would be like 50 times 0.70 times 0.30. Pretty straightforward. Your standard deviation is just the square root of n times p times q. So far, the calculations haven't been terrible. You can throw them in a calculator and get the answer. Now let me show you all the parts and pieces for the probability of a binomial distribution. We need n, we need x, we need p, and we need q. Now the cool part about this is most calculators have this front part, this n factorial divided by n minus x factorial times x factorial. That is a special key on most calculators, but you can do this pretty much long way. And I'll show you in just a little bit how to do this the long route, and then I'll show you how to do it the shortcut route. It is n factorial divided by n minus x all factorial times x factorial. That is all times p to the x power times q to the n minus x power. Now remember, n is just the number of things that we have. X is that value that we have selected to figure out the probability for, like 3 out of the 50. The bottom x factorial is we want to delete the duplications in our trial. P is the success, Q is the failure. And n minus x is the number of failures you have, x is the number of successes. What's the probability that 3 will turn in their homework out of the 50? Then 3 are the successes. And that means 47 would be failures, by the way. Here's our example. I'm not going to give you any story behind these numbers or anything. I'm just going to concentrate on the numbers. N is 30, P is 0.23, and X is 3. So we want to find the probability that 3 are successful given a success rate of 23% out of 30 people. Our equation is going to be n factorial divided by n minus x factorial times x factorial, all times p to the x, q to the n minus x. Now I am going to just start putting in all these values. N is 30. N minus x, that's 30 minus 3. X again is 3. So far we have 30 factorial over 30 minus 3 factorial times 3 factorial. P is 0.23. X is 3. Q is 0.77. N is 30. X is 3. We can combine a few of those things and get it at least to look like 30 factorial over 27 factorial times 3 factorial times 0.23 to the third and 0.77 to the 27th. Now I'm going to do this longhand just to show you that 30 factorial is going to be 30 times 29 times 28 times 27 factorial. I have a 27 factorial down below, so I'm just going to take that 30 down until my largest factorial in my denominator, because ultimately those will cancel out. Now I can even reduce it further. I'm not worried about the power stuff yet. I'm going to get rid of those factorial of 27, and I get 30 times 29 times 28 all over 3 times 2 times 1 times 0.23 to the third times 0.77 to the 27th. That, at this point, is a calculator problem. I'm going to be very careful about putting it into the calculator. I'm going to use parentheses. Once I do that, parentheses 30 times 29 times 28, parentheses, divided by parentheses 3 times 2 times 1 in parentheses times 23 cubed times 77 to the 27th, I am going to get 0.0426. That's doing it longhand. And granted, you might mess up a few times before you get the hang of it, but that's doing it kind of longhand before I can put it into a relatively simple calculator to calculate it out. Even if I had a TI-30X, I will say this first part of the n factorial divided by n minus x factorial times x factorial, that goes by a particular name, and it's called a combination. A combination will look like n, a small n, a big C, and a little r, where n is the number in, just like ours, and x, in this case, is an r on your calculator. You can think of it as NCX, but on the calculator it's NCR. On the TI-30, you would go to probability. Here's how I would key it in just for that front part. 30, hit the probability key, find NCR, then hit 3. And then do the rest of it. 0.23 cubed times 0.77 to the 27th. Hit enter, and it gives me the same value. Enough of working it out longhand. I want to use the TI-84 to work out this problem. It has been stated that about 41% of adult workers have a high school diploma but do not pursue any further education. 20 adult workers are randomly selected. Let X be the number of workers who have a high school diploma but don't pursue any further education. So X will take on the values of 1, 2, 3, all the way up to 20. Now we do have to pull out some information. Our N is our 20. Our P value, well, that's the number of success, the probability of success, which is 41% or 0.41. Our Q value is 1 minus the 0.41, which is 0.59. Now, I don't even need that part. I just need N and I need P to be able to figure out what it is using the TI-84. Now, we want to figure out the probability that exactly 4 of them have a high school diploma, but do not pursue their education any further. We want to figure out the probability that at most 12 of them have a high school diploma, but do not pursue any further education. And 3, we want the probability of at least 15 of them have a high school diploma, but do not pursue any further education. So if it's exactly 4, we're going to use P of X equals 4. If it's at most 12, then it means it could be 0, 1, 2, 3, 4, 5, all the way up to 12. So X is less than or equal to 12. So we need to find the probability of X is less than or equal to 12. And if it's at least 15, then it means 15, 16, 17, 18, 19, 20. So the probability that X is greater than or equal to 15. But remember, calculators don't do that. They only use less than. So we need to say 1 minus the probability of X is less than 15. For the TI-84 plus working with binomial distribution, we do have 2 functions that we will use. The first one is called binomial PDF, probability distribution function. The second is binomial cumulative distribution function, which is CDF. The difference is when you are going to use them. When you have something like the probability that X equals 2, that X equals is exactly 2, then you would use PDF. If you are in a situation that the probability you're looking for is X is less than or equal a value, like probability that X is less than or equal to 10, then you will use CDF. And if you're looking to answer a question that your value is the probability that X is greater than a value, then what you're going to have to do is a little bit of math on top of the CDF. The CDF only takes care of less than or equal to. We're looking for greater than or equal to. But the cool thing about it is we know all probabilities add up to 1. So if we do 1 minus the probability that X is less than that value, then we're going to get the right answer. So if it's equal, you use PDF. If it's less than or equal to, you use CDF. And if it's greater than or equal to, then you're going to use 1 minus the CDF. So let's see it in action. We have an example going on, and we want to find the probability that exactly 4 of our selected people have a high school diploma but do not pursue any further education. Our N is 20, our P is 0.14, and our X value is 4. Because of that, we're going to use PDF. So second vars, which is the distribution right up here. And there's a whole long list of them to choose from, and you're going to find the one that's the binomial PDF. Right underneath it is CDF. We're looking for PDF, which is an A. If you remember, A goes along with PDF, B goes along with CDF. I'll show you a shortcut way of getting there. So we want A. Our number of trials is 20. Our p-value is 0.41, and our x-value was 4. We paste it to our screen, and we hit enter for it to calculate. So the binomial probability is for that x is exactly 4 is 0.295. Now you might be wondering, hey, how is your decimal only showing up with 4 places? Well, that's because I actually put that setting on. So if you go to mode and you change your float value, the float tells you how many decimals you want. If you want your decimals to be rounded to the 4th place, just put it on 4, and that should do it for you. Okay, so let me get out of here. Let's go back to our problem set. So that was when it was exactly 4, I used PDF. Now what's the probability at most 12 of them have a high school diploma but do not pursue any education? So at most means that it could have been 0, it could have been 1, could have been 2, could have been 3, could have been 4, could have been 5, could have been 6, could have been 7, could have been 8, could have been 9, could have been 10, could have been 11, could have been 12. If we use PDF, we're going to have to calculate 12 of those and add them all up. We don't want to do that. We want the computer to do a lot of work for us. So this is CDS. So the binomial distribution function, if you say it's cumulative, it's going to take from 0 to that value and add them all up. So second vars, and I said there was a shortcut way of getting down there versus toggle down, 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 down. It is alpha B. Here's B right here. So alpha B, and that will get you to binomial CDF. Trials is 20. Our probability that it's a success, our p-value is 0.41, and our x-value is less than or equal to 12, so it's 12. And therefore, 0.9738 is our probability that at most 12 of them would have high school diploma but no further education. So let's find the probability that at least 15 of them have a high school diploma but do not pursue any education. So if I straight off use the binomial cumulative distribution function, so second distribution, alpha B, and changed our value to 15, we would get 0.9996, but that would be less than or equal to 15. So I'm looking for more than or equal to 15. So I have to say 1 minus this binomial CDF value, 0.9996. And that gives us 4 to the negative 4. In other words, 0.0004. Okay, 1 minus that. Make sure when your answer has this E value, that's in scientific notation, you got to move your decimal 4 places. So it's 0.004. Now, if I did not want to do that in 2 different steps, I could have automatically said 1 minus the binomial distribution. There we go. And that makes it do it in 1 step. Now it gives us some more decimals here, but remember we're moving the decimal places 4 spots, 1, 2, 3, 4, and therefore your answer would be 0.12344315, rounding to 4 decimal places, so 0.0004. So that's it for using your TI-84 plus for the binomial distribution. Just as a reminder, if it is x equals a value, you'd use binomial PDF. If it is less than or equal to a value, then you'd use binomial CDF. And if your value is x is greater than or equal to some number, then you would use 1 minus binomial CDF. And that's it for now. Until next time, be seeing you. You've reached the end of this lesson.